Thank you very much for the invitation. And as some of you might know, I really don't deal well with this non-interactive thing, right? When I just talk into this outer space. So please interrupt and ask questions. Also, this is based on one of my general talks. So if somebody saw at least part of this, I apologize, but there are some new pieces that I added to show how this program develops. So my goal is to talk about different functional inequalities. And of course, we have experts in the audience, and I'm not really, but I'm usually interested in a very specific application of this related to the behavior of measures in infinite dimensions. So this is your height dimensions here, right? So my goal usually is to do things in infinite dimensions, though I tried lately not to do it, but somehow I'm forced into this infinite dimensional spaces usually. So one of the, so I'll start with a very simple application of a simple inequality. And yes, it goes back to Langevin, but before that, I just want to list several inequalities and the kind of properties that I usually have in mind. And we will not touch on most of these consequences that you usually see, but I just wanted to keep this in mind. So, so the first inequality that I'm usually mentioning here is Sobolev, and this is why his name is in green, I guess, right? This is your typical inequality here, where the thing is that really bothers me is that the constant depends on the dimension of the underlying space. And of course, if you're trying to do anything in infinite dimensions, this is the first thing that is a problem. Yeah, of course, there are lots of problems with this type of inequalities, including the reference measure that we might be able to deal with, but this dependence on the structure of the underlying space, including the dimension, is something that we want to tackle eventually. And of course, this type of inequalities have lots of applications, including in PDEs. And again, if you're moving to infinite dimensions, this is something that you cannot rely on. So this is why we usually use probabilistic techniques even to construct the objects that make sense there. So I just mentioned it here. So my goal eventually will be not just to move to higher infinite dimensions, but actually to introduce some geometry, and actually geometry that I would be interested in is not even Riemannian geometry, but more like a degenerate geometry, Subramanian geometry, or in general, hypoelliptic diffusions. So this is what I will be doing. I will be adding dimension, curvature, and then Subramanian or degenerate structures gradually. So we'll have this combination of all of this at some point. Okay, so if we replace the this underlying space by Riemannian manifold, that still is okay because you just replace the usual Laplacian by an elliptic operator. So you take the Laplace-Beltrami operator, and then you can still use this classical techniques of, say, to prove elliptic harmonic inequalities. Again, so you rely on Sobolev inequalities. That's the typical thing. Using Moser's iteration, you prove this harmonic inequalities. So there are lots of connections between all these inequalities. And so, for example, when I, some months ago now, talked about this uniform doubling properties on SU2, I did talk about how you have some of these inequalities and what kind of implications they have for all these different combinations of things, right? So if you have some, so the geometry can be described by the volume growth. And if you have Poincare inequality, then you can prove Sobolev inequality. And lots of these things are either equivalent or imply one another. So essentially, if you know a lot about the underlying space, that is either curvatures, as we'll see later, or volume growth, and you have some basic inequalities like Poincare inequality, if you have this control of the constants, you might be able to prove this other function inequalities. I also want to mention here that there are also very clear implications for the spectral properties of the corresponding operator. And this is what I'm mentioning here. But we will not talk about this because these things become really not tractable in infinite dimensions usually. But in finite dimensions, we are still interested in this, and I will not talk about some of these things that you can still do for these hypoelliptic operators in finite dimensions. So some of the applications, so if you move away from manifolds, Riemannian or Subramanyan manifolds from Euclidean space, the usual application for these methods would be to Markov semigroups. And in that case, you would look at functional inequalities, but with respect to an invariant measure. So your reference measure instead of the this Lebesgue measure here, so that was Lebesgue measure here, you replace it by something, if you're lucky and you have that invariant measure, you replace it by that. And again, these methods usually work to some extent. Okay, so the one application that I hope to mention, which will be a new piece for this whole survey talk, is ergodic properties of the semigroups, and I will talk about infinite Langevin dynamics. This is recent work with Fabrice Baudoin and David Herzog, and this is really finite dimensional, but with the hope that we can do it when you have infinitely many particles at the end. Okay, so the summary here is that to describe the geometry behind all of this, you really need to know something usually about volume doubling and quite often curvature bounds, such as the Ricci bound, okay? So the inequality that will be deals with this problem of having the dimension in the constant, of course, is the classical log Sobolev inequality, which is due to Lamb growth in Euclidean space with the Gaussian measure mu. And so that's the classical version of this for manifolds, for Riemannian manifolds, where the constant does depend on the Ricci usually, but the dimension is not there. And I want to mention here that it's not posted yet, but there is a new result coming for Subramanian manifolds, actually for Heisenberg groups, and with, again, the application in infinite dimensions. So, so student of mine, PhD student, she is finishing this work. So we have one preprint, which is not posted yet, and another one that will be applicable in infinite dimensions, where, of course, you don't have this Ricci curvature bounds. Okay. So, again, the applications, why people were interested in this inequality at that time was this application to hypercontractivity, also finding spectral gaps. So as you can see, all these properties of spectral properties and this function inequalities, of course, as we all know, I'm preaching to the choir here, are connected, right? So I don't need to convince you that we should really study them, right? Because they're fun. Okay, so here's the application that I have in mind, and more or less this is was behind some of the results that I'll be talking about later. So this is really a very simple application of this observation that the Gaussian density behaves in a certain way under the translations. So we start with the normal density with the Gaussian density here, standard one on Rn. So we take the Gaussian measure, and then we take what's called log derivative of that, right? That's what you have here. Yeah, of course, in this case, you can simply compute it. This is what's written there, right? So H is your translation or direction of the derivative, and X is the point that you fix. So yeah, of course, you cannot really distinguish between these two things here, but in general, X is your point in the space, H is the direction of the derivative. And then you can actually compute directly this thing. So usually in more complicated situations, you don't have this direct computation. You have an estimate on this log derivative with respect to the Gaussian measure. And then what you see is that if you take the heat kernel or the Gaussian density shifted by H here and compare to the original density here, and then you take the LP density, LP norm of this with respect to the Gaussian measure, you have this estimate here. Okay, so what's the, why is it called integrated harmonic? Because yes, you shift one thing with respect to the other, that's your harmonic, and then you integrate with respect to the reference measure, which is the Gaussian measure here. So why is it interesting? Well, we'll see an application for this, but the main reason why I'm interested in this is because this thing here doesn't have any dimension, right? So you have your exponent P here, you have the norm of the shift H, but there is no constant that depends on the dimension. And so once you have this kind of estimates which are uniform in the dimension, it means that you might be able to apply it in infinite dimensions. Okay, so here's the one proof I guess we have for this talk. I think it's the only proof. And yeah, I will not really comment on this because yes, you can just compute things, and instead of that inequality that I had here, so this is not an inequality, it's an equality, but I just wanted to kind of emphasize that in general, what you might do, you might take this density shifted, and I will be doing this on Lie groups, so it will be multiplication rather than subtraction like this. And once you can compare this density and have this estimate, you have these applications that I'm interested in. Are we still okay? Kind of, yeah. Okay. Okay. So what's behind it? What's behind this proof also is that the Gaussian measure is not translation invariant, but it's quasi-invariant, as we call it in this business. And what it means is that if you translate your measure, so since I like infinite dimensions, I usually think of this as a measure and the whole thing. So I shifted by H, and I acquire the Radon-Nikodym density, which is an LP, and actually I have nice estimates for LP norms for this. That's the kind of moral of the story for now. Okay. So here's your classical application for this, which is the Cameron-Martin or Gersanov theorem. So we start with abstract, well, in this case, classical Wiener space, the space of continuous functions on 0, 1. With the subnorm, you have your Cameron-Martin subspace H, a Hilbert space, densely embedded into W, so it has a different norm there. You take the Gaussian measure on W, which you can define by its Fourier transform. And so you have this triple, which is an example of an abstract Wiener space. So it's a triple of Banach space, Cameron-Martin Hilbert space densely embedded into W, and the Gaussian measure mu. Okay. So one of the things that we should keep in mind here is that the Cameron-Martin space becomes a set of measure zero. So there are some nice quotes of what Landgraf wrote about this when he was writing tribute to Irvin Siegel of the role of this Cameron-Martin space, which we will not really talk about right now, but just let's keep that in mind, that the analysis on W is usually governed by the smallest set of directions from H. So here's the proof. Here's the theorem that I mentioned on the previous slide, which says the following thing. So now what we have here, we have this Gaussian measure, but you cannot write it anymore as the density with respect to something like the Lebesgue measure. We don't have the Lebesgue measure, right? So how do we understand the shift here, the translation? Well, what you do, you write this weak kind of formulation where you take all reasonable functions f here, translate the variable here. So W here is from this large Banach space, translate by H from the Hilbert space from the Cameron-Martin, and what the theorem says that actually you can push it to the measure here and you acquire the density with respect to the original Gaussian measure. So this is what we usually call the Cameron-Martin type result, or Girsanov type result. And actually you have this LP estimate here. So this really resembles, so this is really an inequality now. It's not an equality as we had before. And again, the proof for this, which I think will be the second proof, really only uses those finite dimensional estimates that I mentioned before. So the takeaway from this theorem, besides this classical theorem about Cameron-Martin Girsanov type result, is that the right-hand side is finite only if this norm is finite. Okay, so that follows from the proof, and actually what you see from here is that really you can only expect this property from the measures, from the translations by elements from this set of measure zero, which is the Cameron-Martin set. Okay. So the proof goes, I will not spend too much time on this because I really want to move on to other things, but essentially if you can define reasonable finite dimensional approximations, which you can from this abstract linear space structure, all you have to do is to carry on this finite dimensional approximations here and then see that it all reduces to the kind of estimate we had. Remember the translation. So these are just normal densities here, Gaussian densities. We had the estimate before the LP, and this is what we use. And what you see from this estimate that you can only hope, it's not a proof but of that, but you can only hope for this to hold when this H, the translation, is from the set of measure zero from the Cameron-Martin space. So this is a very infinite dimensional type of result, and that's the end of this proof. So really what I want us to remember from this is that this quasi-invariance carries on to this infinite dimensional setting because we have the Gaussian measure, and it only is true for these translations by elements from the Cameron-Martin subspace. Okay, so why people are interested in quasi-invariance? There are lots of reasons for this. First of all, we understand it as smoothness of measures in infinite dimensions. That is when you cannot write your measure as having density with respect to some reference measure like the Lebesgue measure. You use it to prove lots of regularity results about SDs or PDs in infinite dimensions. So you use it to prove lots of useful things like closability of the gradient and things like that. So here I do mention usually some work with that we had recently with Michael Rockner and other people on this. But I will not talk about this. Another thing that I really want to mention here, maybe because I still have things that I need to finish there, is that this quasi-invariance of the measure actually produces unitary representations of the group that acts on the space X. Okay, so this is the subject that came from math physics, and it produces unitary representations of these infinite dimensional groups when you actually don't know how to characterize them or how to describe them in some other ways. Okay, so usually this is applied to path groups, and again, we will not talk about it in this case. So now, since we went to these infinite dimensions, I usually want to go back to finite dimensions. And as I said before, what I want to do is to introduce different geometries on the underlying space. So if we think about, instead of Rn, if we think about R3, what we looked at was really flat geometry here. So we had Gaussian measure, we had the three-dimensional Brownian motion, right, which is connected to the Gaussian measure here. So the Gaussian measure is the law of this Brownian motion. And the generator here is your usual Laplacian, okay? Plus or minus 1/2, doesn't matter, the Laplacian, okay. So what we'll do, we'll take this R3 and equip it with three different geometries. So one was flat, another is the Riemannian geometry, which is not flat. And you can do it by introducing these three vector fields. So what I'm aiming at is to look at what's called the Heisenberg group. So in this case, the Heisenberg group is just R3, which has the structure of this group with a funny multiplication law, which I might mention later, not right now. So what you do, you take three vector fields on this R3, and then you solve the stochastic differential equation. So it's driven by three Brownian motions here. And the difference between what we saw on the previous slide is this correction term here. So that's the Levy stochastic area here, okay? So this is an implicit, it's an explicit way to solve this SD. And actually, if you look at the law of this Brownian motion, it gives you a smooth measure on R3. It actually is the usual Brownian motion on the group, Heisenberg group, equipped with the Riemannian metric. So in this case, this operator, so that's different from what we saw for the usual Brownian motion, is an elliptic operator. Okay, so now we have two geometries on our R3, and the third one is the simplest example of so-called Subramanian geometry, which is based on the following observation. So if you look at those three vector fields, I can remind you what they are here. So these are three vector fields. You can take a lip bracket of these two, and you can check that the only lip bracket which is not zero is this one here. Okay, and this is really an indication that this system of vector fields satisfies what's called Hermander's condition. So this means that at any point in your R3, this X, Y, and the lip bracket of X and Y generate the whole space. These are linearly independent, three linearly independent vectors. Okay. So then we can solve a very similar SDE to what we had previously, except that, as you can see here, what we've got is we have only two independent Brownian motions. We don't have the third one, and the component you have in the last here, what it is just Levy stochastic area. So seems very similar. And at this point, you don't see a huge difference in what we had before. The difference is that, yes, mu t, the law of this stochastic process is a smooth measure on R3 by Hermanter's theorem of 67. But the generator is not an elliptic operator, it's a hypoelliptic operator. So it has the smoothness properties, but all the PDE techniques that I mentioned in the beginning of the talk, they are not applicable easily here, okay? So the geometry that corresponds to this operator is not Riemannian geometry, it's Subramanyan geometry. Okay, so just to recap, what we've seen was that besides the usual flat space on R3, we have two geometries on R3. So as you can see, the Heisenberg group in this case is just R3 with this funny law where you have the usual addition for three components plus the correction term, which is given by standard symplectic form. And the corresponding two Brownian motions I had were elliptic Brownian motion and hypoelliptic Brownian motion. And the corresponding analytic properties of the generators are very, very different. And geometries are different. Okay, so next I'll go very kind of quickly over the standard approach to geometry of elliptic diffusion operators. So that's, of course, due to Bakri, Emery, Ledoux. So the idea is, of course, to not think about the underlying space M, but just look at the operator itself and define the geometry by looking at that operator. So you take your Carré-Duchamp operator here, you iterate that, right? And then you say that this operator, and of course I skip all the analysis here. I don't talk about, you know, the domains or anything like this, right? We're just doing this formally right now. Then we say that this operator L satisfies curvature-dimension equality with constants K or kappa and M if this is true for any reasonable function f. Okay, so why did I write something like this here is because really, I really want to get rid of geometry and I don't want to explain what Ricci curvature is, for example, right? So this gives me a way to define it without really giving you any definitions of in Riemannian geometry. So as long as you know that this is equivalent for Riemannian manifolds, this is our take on this. So you just take your operator L and try to find these two constants. Okay, we still okay? Okay. So the two examples that I want to keep in mind for this is the Laplacian we had on R3 or on Rn, where of course you can compute all of this explicitly, and then you see that as expected, it satisfies the curvature-dimension equality 0m. So m is really the same dimension as the underlying space. Curvature corresponds to this being flat space. So that seems to be reasonable, right? Another example that we should really keep in mind is the Unstained-Uhlenbeck process. So it's given here. You see that? And if you do this whole iteration there, so you get to gamma 2, and you can easily show that this is true, right? And what you see now is that it satisfies the curvature-dimension equality with curvature being 1 and the dimension being infinite. Okay, so even though the underlying space is finite dimensional, it's one-dimensional, the interpretation for us is that this operator has this dimension equal to infinity. Okay. So why do we care about this curvature dimension equality? Because yes, it does imply lots of nice functional inequalities that we're interested in. And here's a sample of those. So, so first of all, as again expected, right, if you have Ricci curvature bound infinite dimensions, you should be able to get log Sobolev inequality, right, as we had in the beginning. You can, for zero curvature gain is the curvature of the operator, not necessarily of the underlying space. You get Li-Yau inequality, so this is written here. Heat kernel estimates that I don't really write here because we're not going to talk about any of this. And also you can prove something nice, which is like parabolic harmonic inequality. So you have a huge machinery that really gives you, like, if you can prove this kind of curvature-dimension inequality, then you can prove this collection of functional inequalities, and then you might be able to do something with them, right? Okay, so the one application before I'm going back to the Subramanian or hypoelliptic operators is what happens if you put the infinite dimension. So this is a relatively old work with Bruce Driver. And what we were interested in was how you do this on infinite dimensional groups, Lie groups. Okay, so I don't remember where I stole this picture from, but it was recently that I did this, but I somehow don't remember. But essentially, what it shows how you introduce the distance. So what we looked at was the following. So you take a Lie group, so finite dimensional Lie group. Unimodular means that the Haar measure on that is bi-invariant. That's equivalent way of saying this. So it's invariant on the left and right translations for multiplication. And what you do on the Lie group, you take the tangent plane, say at the identity, and you use left-to-right multiplication to move this tangent plane. And at the identity, you identify the tangent plane with the Lie algebra. And what you do, you equip that Lie algebra with an inner product, and that determines the Riemannian distance on your curved space here. Okay, so the Riemannian manifold that we're looking at here is really this Lie group, which has this left invariant structure on that, or actually in this case, bi-invariant structure. And what we want to do is we want to see what happens if we take a sequence of these groups when the dimension of the group goes to infinity. So the theorem that we proved was the following, and this is really an analog of this Gaussian estimate I had in the beginning. The Gaussian, remember what I had here was x minus h, right? So x, y inverse is exactly x minus h in this case. Okay, so what it says is that suppose you have group here, and you can compare the shifted heat kernel measure, heat kernel in this case, to unshifted one. So it's exactly the same thing that we had before. And then you take the LP norm with respect to the heat kernel measure. So in this case, it's not Gaussian, but the analog of that, which is the heat kernel measure. Then you have this estimate here. So what's interesting about this, again, the dimension of the group is not there, right? So that's good news. The constant here depends on the curvature bound here. So reach a curvature bound here. So essentially the outcome of this theorem was that if you have this kind of bound uniform for all for the sequence of your groups, then in the limit you might be able to prove something like this, and we used it to prove quasi-invariance result on an infinite dimensional Heisenberg group in this case. So this
I had a quick question.
Yeah.
Yeah. You said earlier that you're going to use the equivalence between the Ricci curvature being this lower bound on the Ricci curvature and some statement on the generators. So I mean, here now you're using the Ricci curvature, you're not stating it in terms of a generator. What's the equivalent way of thinking about it in terms of generators?
Yeah, so I'm not stating it in that way, but you can actually do it in this case. So the Laplacian here is, so for at least a simple case for, say, matrix Lie groups, the Laplacian you would have here is a sum of second derivatives. So something like this. So you take a function, I don't know, maybe I'm not answering your question, but because I didn't say anything about the operator here, but it's the same as the taking the Laplace-Beltrami operator in this case. So what you do, sorry, I don't know if you can see what I'm writing. It doesn't seem to be very legible. So you take a point in the group here, G, you move it along exponential, so you can think of this as a matrix exponential. That gives you directional derivative of function at point G. You can do it twice, and this is your Laplacian. So in this case, you can write this Ricci curvature bound equivalently exactly the way I wrote this for the curvature dimension equality. I just didn't want to write this, but the dimension is not going to be there. I don't know, did I answer your question?
Just to be sure, I mean, so this result holds for any generator that implies
No. It's for
or
this
is it very
particular
specific, this generator?
This Laplace-Beltrami operator, more or less, yeah.
Okay, thanks.
So when we say that the this Lie group has this Ricci curvature bound, usually we mean that the Laplace operator defined this way, for example, has this bound. Okay, so it's not for any, so we don't have a drift here. It's really for that. Okay, are we okay with this?
Yeah, thanks.
Mm-hmm. Okay, so this estimate actually is sharp because it really produces the exactly the result that we had for Rn. And this is dimension independent, and therefore it has applications to infinite dimensional settings, as I said. So let me skip this. So the applications we had actually was not just for this Heisenberg group in the elliptic case, but also for lots of results so we were able to recover some of the results that people got before that in infinite dimensions. And but this also, we did this when we introduced this infinite dimensional Heisenberg groups. So see that I'm running kind of slow, so let's skip some of that. And what I want to mention now is what happens if you actually move to the Subramanian geometry. So that was actually Riemannian geometry. So you can take it to infinite dimensions and the curved space. So this whole machinery of Bakri, Emery, Ledoux really fails when you try to apply it to hypoelliptic operators. And this is a typical example of this, what usually Fabrice used to show, that you have this mixed terms, and you can prove that you cannot control them even in the simple case of two generators like X and Y. So you can prove that no matter which constants K, kappa, and N you take, the curvature dimension is not going to hold, and therefore it seems that you should do something else. So what Fabrice Baudoin and Baudoin-Garofalo did some years ago, they introduced what's called generalized curvature dimension inequality, which is not applicable really to all kinds of different settings like this, but at least for some hypoelliptic operators or Subramanian manifolds, you can use that. And so what we did, so remember, I wanted to move to high dimensions or infinite dimensions with not necessarily even Riemannian structure, but Subramanian structure. So the first result of this kind was that we proved with Fabrice Baudoin and Melcher in 2013. And it really takes this infinite dimensional Heisenberg group that I did not define, but I can explain what it is later on if we have time. And even though we don't have this machinery that we use with Bruce driver, or we don't have uniform Ricci curvature bounds, we were able to prove some limiting inequalities, functional inequalities, such as reverse log Sobolev and reverse Poincare. So we couldn't really prove log Sobolev itself. So this is a result. So reverse really is the result of not having curvature-dimension inequalities, but rather relying on this generalized curvature-dimension inequalities. But the one thing that survived was that integrated harmonic inequality for the shifted heat kernel. So you have hypoelliptic heat kernel there. And this allowed us to prove quasi-invariance of this hypoelliptic, subelliptic heat kernel measure. So why was it significant? Because for some years now, for those of us who know about hypoelliptic operators, if you think about the definition of hypoelliptic operator as was maybe used by Hermander, it really relies on Rn. You cannot really take that definition even and move it to infinite dimensions. So it's really not even clear what hypoellipticity means in infinite dimensions. So as I said before, quasi-invariance can be viewed as smoothness of these measures. And so if you have this kind of result for something that looks like hypoelliptic object, the hypoelliptic heat kernel, that gives you a way to say that, yes, we have this degenerate geometry or degenerate behavior of the operator, but we still have the smoothness that you expect from a hypoelliptic operator. So that's the replacement of that. Later, Bruce Driver, Nate Eldridge, and Ty Melcher gave a different proof, which relied more on multivariate calculus for this result. And there are some other developments that we still don't have any results, so I will not talk about that. There was also a different approach to this infinite dimensional hypoelliptic setting that we developed with Fabrice and his PhD student, Chi Feng, which is very geometric. So but we proved quasi-invariance and integration by parts, things on path spaces and things like that. So I'll finish with a very, very different setting, very different hypoellipticity also, which I hope might be interesting for some of you. So if you're not into this geometry things, but something like this, maybe it will appeal to you, because also it, again, gives some connection to ergodicity, for example, of this system. So here's the setting. So this is a hypoelliptic system of the Langevin dynamics. So this is a joint work with Fabrice, Baudoin, and David Herzog. And again, as I said, in principle, what we want to do is we want this, oops, did I say? Yeah, the number of particles to go to infinity eventually. But for now, the constants still depend on that, so we still need to do something about that. So here's the setting. So you have this system of equations. So so the usual momentum and position system here. And the interest for us is, so this is just a Brownian motion. So as you can see, it only, so you have the noise only in half directions of your space. So this is your state space, right? And the noise is moving only in half of those dimensions. And what we will be interested in this potential. So we want this potential not to be so nice. Okay, so there are a bunch of constants here, friction and temperature. And the reason why I mentioned this, because we also want to keep track of constants, how they depend on this parameters here. Okay, we will not see it, but that's what we're interested in. Okay, so what we want to look at is really look at the potential that has singularities, such as the Leonard-Jones potential. And in this case, you know what the invariant measure is. So it's known explicitly. So this is your Gibbs, Boltzmann-Gibbs measure here, written explicitly. using the Hamiltonian. So this is the potential that you're given. And of course, physicists would write it like this. So this is your Langevin equation. And once you write it like this, you know what each part actually indicates or describes in this physical system. Okay, so what are we interested in? We're interested in convergence to the equilibrium, that is to this Gibbs measure. We want to see in which sense you have this convergence, and we also want to know explicit rate of convergence, that is how it depends on all these parameters and on the potential.
Sorry, how do you know that even a solution exists when you have singularities? What
that
theory
comes
do you appeal
from,
to?
yeah, it comes from the work that was done before, yeah. So we didn't have to worry about that. I can give you references later, but not right now, probably.
So there
okay.
exists an infinite time solution to the
yeah.
ST?
So it's not something that we have to deal with, yeah. And the invariant measure is known too, so that's not new. It's not what we did. Okay, so the kind of potentials we're interested in of this sort. So there are 3 examples here, including the Leonard-Jones potential here, and actually the so the dots here indicate what was known before, like what people could do. And these are the kind of things that we actually can tackle now, but I don't think was done before. Okay, so the potential usually consists of 2 parts, which you separate. So I definitely don't have time to talk about this. So what I want to do is to formulate the result, which unfortunately takes a little bit of time to even formulate. But before that, I will mention that the 2 techniques we're using is really this more kind of local curvature-dimension inequalities, plus this Lyapunov function approach, which comes from the work that people did before that. So depending on the potential you have, you define some compact set where you do this curvature, more geometric method of controlling the system, and outside of that, you construct a Lyapunov function in a typical way of taking the perturbation of this Hamiltonian that I wrote explicitly there. So here I list some of the work that was done before, and of course, the work that at least previously I was trying to adopt here, and which is related to what we did, though we didn't use this method. So it's hypercoercivity, which is due to Villeneuve. And also, I usually mention this work here because as you will see on the next slide, we do use weighted inequalities here. So we adopted this, and then we use the curvature-dimension inequality for that. But outside of this compact set, we used this technique here. So we combined the 2. There is also work of Eberle with co-authors also giving explicit rates of convergence, but they assume bounded derivatives of the potential, or Hessian being bounded, which rules out the potentials that we're interested in, and also that we can tackle. So this looks horrible. So let's not pay too much attention to this. So the main thing here is here. So what you do, you take the Gibbs measure here, and you put a weight on this. And then we use some of these geometric techniques to guess what this weight should be for to be able to control. So this is a weighted Sobolev space that we use. This you do on subspace of your state space. So it's determined by the potential that you have. And once you have this, oops, what's going on? The main slide is gone, right? Yeah. Okay, let me just write it quickly. Okay, I'll write it here. So, so the result is the following. Sorry about that. Oops, is it disappearing now? Yeah. Technology. Okay, so let me do this thing. Okay, can you see it now? So I cannot use my pen on that computer, but essentially this is the result. So what we want to emphasize here is this thing here. So what it says is that we have geometric convergence to equilibrium. So sigma is an explicit constant. So all the constants here explicit, which depend on the potential and the constants, the dimension, and yeah, I'm trying to multitask and this is not good, right? Okay, I'll just concentrate on what I'm trying to say. So the constants here depend on the dimension, on the friction and temperature constants parameters, and you can write them explicitly. So what we did, we took this Lennard-Jones potential, we took a couple of other examples where we can write explicitly all these constants. So this sigma is positive, and so when time goes to infinity, of course, you have this convergence to equilibrium. So the function here is taking so that its average is 0 with respect to the invariant measure. And so that gives you this geometric convergence to the equilibrium. So the kind of punchline here is really it uses these two different approaches together, and this really allows you to deal with this very singular potentials.
Can you understand, just a quick question on this theorem. Can you understand from this theorem whether the singularities enhance or impair convergence to equilibrium?
So, so I think the main examples we
right,
have.
Because so what you could do with the Lennard-Jones, and this is commonly done, is to truncate it.
Yeah, so we
at a certain energy level. So, but what's the difference? Does the singularity enhance or does it impair convergence to equilibrium? Can you, is that clear from your analysis?
Yeah, so if you take a potential of the kind x to a plus or minus 1 over x to b, where a and b are positive constants, you can write explicitly how this rate depends on those parameters. So I don't know if it answers your question, because
no, it doesn't answer the question. So I asked, does it enhance or does it impair convergence to equilibrium, the singularity? The presence of singularities in the interaction term, does that enhance or does it impair convergence to equilibrium?
I'm not sure I understand the question, because really the point is that,
well, you can have the interaction term on or off, right?
Yeah.
And so if you turn it on, do you get an enhancement to convergence? Does the convergence rate, is it indifferent to it? Does it change? I mean, does it get better or does it get worse? I mean, it's a really simple question.
Worse than what?
Worse than the unperturbed case where you have no interaction. So, I mean, if you turn on the interaction where you have the singularity there, does that enhance or does it impair convergence to equilibrium?
If you understand it like this, it does enhance, though I don't think we really should compare it to no potential at all, right?
No, I didn't say no potential at all. I said no interaction.
So if you compare it to different potentials, yes, I would say it usually enhance, but I don't know it really, we should look at two particular examples to see what you want to compare, right?
And your theory actually quantifies that?
Yeah. So the point is that if you give me concrete potential, you can explicitly write all these quantities here. Yeah. And we give examples in the paper. Yeah.
All right.
Where
Thank
we
you.
do the computations.
Thank you.
So it's not like an abstract statement. There exist constants. No, it's really constructing them from the data you have. And in particular, you really need to know, the temperature and friction and the dimension and everything, right? And so it all enters into that. I don't know if I answered your question, but it's very explicit, and that's what we wanted. We didn't want an abstract statement that this constant exists. Did I answer your question?
Well, I mean, you pointed me in the right direction. Thank you.
Okay. I think that's all that I should. I think I ran over time anyway, so sorry about that.